Okay, so this is going to be discussion, beginning discussion about classification. See if I can fix this. So, the outline, I guess, is going to be machine learning and classification, examples, learning as search, bias, and Weka. Not sure if we'll do learning as search. So, finding patterns is often one of the goals of data mining. Programs that detect patterns and regularities in the data. And if you can find a strong pattern, that means that you'll be able to make good predictions. So a lot of data mining is about making predictions, as is statistics often. However, there are three problems listed here. Most patterns are not interesting. Patterns may be inexact, and data may be garbled or missing. So what are the various machine learning techniques? These are algorithms for acquiring structural descriptions from examples. So the examples means we have data, and we're trying to get some kind of deep or meaningful understanding of that data. You can call it a structural description. In other words, understanding the structure of it. Structural descriptions represent patterns explicitly, can be used to predict outcome in a new situation, can be used to understand and explain how prediction is derived. So hopefully not just a black box that can you can put the input in and get the output out, or get the prediction out, but also hopefully to be able to see how that black box is making the predictions, and therefore hopefully understand the deeper structure of the situation or of the data. And the methods from data mining originate from artificial intelligence, statistics, and research on databases. Definitions of learning from a dictionary. In other words, can machines really learn? So what do we mean by learn? To get knowledge of by study, experience, or being taught. To become aware by information or observation. To commit to memory, or to be informed of, ascertain, to receive instruction. So can a machine do any of this? To get knowledge by study, experience, or being taught? Well, part of the question, I guess, is what is knowledge, but I suppose a machine can do that. To become aware by information or from observation. To commit to memory. To be informed of, ascertain, or receive instruction. So the last few are trivial for computers, but the first one is difficult. And here's an operational definition of learning. Things learn when they change their behavior in a way that makes them perform better in the future. And does learning imply intention? Well, not sure. All right, let's look at the classification problem. So there are two kind of general types of problems. One is called classification, another is called clustering. Association is a third type, but it's usually called clustering. So anyway, this is classification. So here you see data, supposedly. And here you have the x-axis, and here you have the y-axis. So here I have a data point, and or let's take this one here, and it's got a large x-coordinate and a small y-coordinate. And so anyway, the way this data is presented, there are only two variables here, the x variable and the y variable. And that's kind of typical for when we want to present data. Usually we only use two dimensions. Now, in addition to those two dimensions, we also see that there's color here, green and blue. And if you think about it, color is, or this color overlay, can actually be used to show a third dimension. In other words, for example, the x might be a person's income, and the y, or actually let's say these were couples, married couples. So the x might be the man's income, and the y-axis might be the woman's income. So a point over here would have a large man's income, but a lower woman's income. So that would be such a couple. Okay, whereas a point over here, or sorry, over here, would have a low man's income and a higher woman's income. Okay, so let's okay, now the color could be something else. For example, whether they own a car or not. So maybe blue means they own a car, and green means they don't own a car. So that's another variable, whether they own a car or not. And we are indicating it with the color overlay. So color overlay can be used to indicate an additional variable. So anyway, but here our task is to identify whether we can find a rule which, given a new instance, so here we have a bunch of instances, and given a new instance, can we use the rule to predict whether they own a car or not? So whether it's going to be a blue dot or a green dot. So we want to develop a model, so to speak, that will do this for us. It will be able to, when we're given a new rule, a new piece of data, a new instance, the model will tell us, oh, I think that this new couple, do not own a car, or they do, whatever. So suppose, let's say, without giving an actual model, but I'm sure that everyone sort of will be able to sort of develop a model in their mind very quickly, in the sense that if I ask you, suppose that we have a dot over here. Suppose we have a dot here, right here. So this is what? A person with low men and high woman. I'm sorry, a couple with low male and high female income. Anyway, would you say that a dot up here is going to be a blue dot or a green dot? So I think that most people would say that it's a blue dot. Okay, so you you're using some kind of model to say that, so to speak. Okay, so what is the model that we're looking at? Well, we might say that there's a kind of a line here, right? And anything above the line we're going to indicate it's going to be blue, a new dot, and anything below this line will be a green dot. So that's the kind of thing we're looking for. So we want the machine to do something like that. So we wanted to learn a method for predicting the instance class from pre-labeled or classified instances. So these are instances, and these are pre-labeled as blue or green. And then once we have that, we want to be able to predict a new instance. So given a set of points from classes here, what is the class of a new point? And there are many different models that we can, or algorithms that we can use to develop a model. As I said, we might just want to put a line here, and that actually could be generated through regression. And there are many other ways. So some of the algorithms that develop these models are regression, decision trees, Bayesian models, neural networks, and so forth. So here we have a dot, a new one, and what are we going to classify it as? Well, there it's kind of on the border, but that might be a hard one to answer. So one form of classification, one algorithm for generating a classification model is linear regression. And by the way, why is it called classification? Well, in this case, pretty obvious why it's called classification, because we're trying to classify, decide which class a new instance is going to be in. Is it going to be in the blue class, the have car, or the green class, the have no car model? Class. Okay, so linear regression. So linear regression here is expressed as a constant plus another constant times the x coordinate, or the x value, plus another constant times the y coordinate, or the y value, is greater than or equal to 0. Of course, we could put y on the other side and divide by w sub 2, and we would have a sort of more standard expression of this. Y equals some function of x, basically, and a constant over here, right? If we bring this thing over to the other side, and also if we ignore this greater than sign, we would have y equals some function of x. So regression computes the w sub i's. In other words, what if we this is, and I think you can see in that case, as I said before, that if I put the y on this side and everything else on the other side, then we're talking about a line. That's a linear function. So then what we want to know is which line are we looking for? Are we getting? So thinking in terms of this picture, we could have a line like this. We could have a line like this. We could have all kinds of different lines. I think probably the best line would be somewhere like this. But anyway, we're looking for a line. So what do we mean by, in terms of the equation, what do we mean by saying we're looking for a line? We mean that we're looking for the constants, right? We know the x and y are there, and then for the constants means like what's the slope and the y-intercept. So we're looking for that. So regression computes from the data the w sub i's. That will give us the slope and so forth. From the data to minimize the squared error to fit of the data. So it's going to choose a line which is sort of best. And what do we mean by best? We mean a line which basically the points are closest to. However, this may not be flexible enough to give good predictions. So we might get this line, and this is the line actually that I was suggesting. Now we get this point, and if we use this point, if we use this line to predict what's the class of this point, not so clear, but I guess we might predict it as green. But you can see it's kind of tricky, right? It may not be such a great prediction algorithm here. Okay, so now we're going to come up with another model. Instead of using regression to generate a model, we're going to come up with another model. Regression would have given us one of those lines, a single line. Okay, so here's a single line. Maybe this is a model we might use. Anything to the right is blue, and anything to the left is green. That's not so great, right? But this part is good, actually. Anything to the right of this line is blue. That actually works pretty well, right? For a point here is wrong, but for the most part it's good. So we could say when x is greater than 5, predict blue. Okay, but when x is less than 5, predict what? It's not really clear. Now, linear regression would only give us a single line. It might give us this line, but it would only give us a single line. However, we're talking now about another way of generating a model. Okay, now what have we done? We said when x is greater than 5, use blue. When x is less than 5, do what? Well, when x is less than 5, think about whether x is greater than 3 or, I'm sorry, whether y is greater than 3 or whether y is less than 3. Now, that's pretty good, because if you say if y is greater than 3 and x is less than 5, you'll predict blue and you'll be pretty accurate there. And if x is less than 5 and y is less than 3, predict green, you'll be pretty accurate there as well. So we have, this is certainly not a linear model, but we have a pretty good algorithm here, or a pretty good model for predicting future cases, it seems. And now we're getting even more precise. So you can see what this does. So if x is greater than 2, and y is less than 3, and blah, blah, blah. So here we have this class, that class, that class, and that class. Or, I'm sorry, those regions, sorry. If x is greater than 5, then blue. Else, if y is greater than 3, then blue. Else, if x is greater than 2, then green. Else, blue. Okay. So this one, according to this rule here, is going to be blue. That's what we would predict. So that is, these are called induction rules, and trees, or tree algorithms, can generate this kind of rule. Okay, now we're going to talk about neural networks, which is another way of classifying. So it's not the regression. It's not linear regression, as we saw before. It's not that if x is greater than this and y is less than that. Induction rules, or trees, as we just saw on the last screen. It can select more complex regions. So instead of just like squares, like we saw in the last one, it can select more complex regions. So it can be more accurate because of that. So it can say, okay, anything within this green shape here, we're going to classify as green. And anything out here, we're going to classify as blue. So it can draw these kind of curved boundaries. It's non-linear, not limited to being linear. However, there's a problem with doing this, and that is it can overfit the data. So in other words, in our data, we're going to probably have sort of a lot of randomness or spurious data, and so, but the algorithm that we use is going to be built on our data, and if it's really closely fit to our data, then it's kind of too closely fit to the randomness, or to some of the random error in the data, and that can be a problem, and that's called overfitting the data. Okay, let's see some examples. Actually, let's stop and continue again.